Now, we don't really care about natural measure itself. We also want to know, what kind of predictions we'll have. So the main thing is that we'll have an observable, a set of observables. And for us, it's crucial that there's no explicit time dependence. So for example, if this is a temperature being measured in Chicago and you keep switching randomly between Celsius and Fahrenheit or something, then there's no dynamical system that can deal with this. So if I have a law that tells me what I'm measuring, observing, which doesn't change in time, I can do this. That means I have an autonomous dynamical system where the law of dynamics doesn't change and the law of observation does. If I produce something that changes in time, I have to extend my dynamics to describe how that happens. So that's a different problem. And I find it convenient to define integrated observable. And the idea is, if I'm moving on a trajectory, I can do my observation as I move along. So I can accumulate my observations. So I can say there is a thing that starts someplace. Let's say x0 goes times t. And the way I define it is I take my observable, I evaluate it on the trajectory, and I get a number. And I'm just, the simplest example of such an observable is the period of the orbit. This is just one, and I go around. And when I'm done, I found the period of the orbit. But in general, I will want to average things in time, so I have to compute their values as a function of time. I find it convenient not to pull out 1 over t. This grows linearly in time. For example, if this is constant, this thing will diverge with time. It has dimensions of time. It's okay. Just convenient. You'll see in a second. I will divide by t very soon. Where x of tau is my law of motion having started someplace. And then I'll be able to define time average of my observable. If it's evaluated on trajectory and went through x0, so every orbit is labeled by 1 point on it, and that will be the limit. T goes to infinity, 1 over t that corresponds. And that's what we do in dynamics. We look at the system as it evolves and we make a measurement on it. So the simplest measurement to do is an average of our observable. And there's a machinery which is same as in statistical mechanics. You can also look at moments of observables, etc. So I can look at, but this is the simplest object I can measure. So that's time average. And it's easy to show, I do it in the book, that if orbit is infinite dimensional and you change the point on it where you're measuring on the orbit, you'll always get the same observable. Because if you change it by finite time, it'll produce a finite contribution which will be divided, go to 0 as in the average. So this is property of the orbit. At the starting point, not actually. It's intrinsic. So if you have some orbit. And the simplest version of orbits that we're aware of are periodic orbits. So if you have a single traversal of a cycle, I'll have average computed on that periodic orbit to be defined as integral from 0 to the period of periodic orbit divided by the period of the orbit, where x x of tau is the element of the periodic orbit. So this could be, in continuous symmetries, you have to think a little bit more about what you mean by the average. But let's assume that we don't have continuous symmetry. And the simplest of all, if I have a fixed point, then AQ is simply a evaluated at a fixed point. So while in general it might be hard to compute reliably this average, you might worry about your quality of calculation because we know that we are not able. For mathematicians, they're happy they go home, but we know we're actually not able to compute this orbit. We only have finite accuracy in computation of this guy. So you might worry about meaning of this, but the beauty of looking at invariant solutions is that it's all finite computation, so you can do them as well as you want.